everyone. Hey. I don't think I have any announcements. Cool. Let's start our class with kind of a step back, and we've started to talk about molecules. We've started to talk about atoms. They exist. The only reason we care about atoms is because they come together to form molecules. So the question is, what are those molecules and how does that relate to this question? So if you haven't got a chance yet, read through this question, see which one of these you think is the most appropriate answer when you're thinking about generics versus a main brand drug. Did you have an unfair advantage? We're learning. No, that's marketing. I don't know how that's done. All right, we have 47 responses. Everyone got a chance to click in? So there's one of the things that you're starting to see is that chemists care a lot what the shape of the molecule is. The shape of a molecule is not just one central atom and 3 or 4 things connected to it, right? A molecule is glucose, 6 carbons, 6 oxygens, and 12 hydrogens. How are those arranged connected to each other? How are they physically arranged in space? If you have a carbon that has an oxygen sticking up into space versus down into space, that totally changes which sugar it is. And so what I want us thinking about is when you take a drug, and if you have a generic drug or if you have a name brand drug, which one of these do you think is the most appropriate answer? Let's have a share out for what you might think, and then we'll discuss why. Sarah?
I said C because sometimes when I look at, I'm use like, when I get like my estimation, I think sometimes when I read the ingredients to see what am I getting, it's the exact same thing, just a couple of different ingredients.
Okay, so what you're talking about is the formulation of the mixture. And so that mixture is multiple drugs. And so if it's something maybe for your skin or something for pain, then it might have 3 or 4 different drugs in it. And that mixture might be different depending on who you buy it from. If we buy a drug, one compound, ibuprofen, for instance, vitamin I, it's my favorite vitamin. If that is a different structure, if there are different atoms connected to each other, or they're even in a different arrangement. If one has a ring with something sticking up and the other has it sticking down. Those are 2 completely different compounds. You can't call them the same thing. So there's examples of birth defects being caused by a compound that is the same exact formula. You look up how many carbons, hydrogens, oxygens, and nitrogens, identical. The only difference is that one has an atom sticking up, another has an atom sticking down, and one causes birth defects, one cures morning sickness. Is it important? Okay, so we cannot say that 2 compounds are the same exact thing unless they are literally identical to each other. So then why would we buy Advil instead of ibuprofen from Walmart or Walgreens?
Tastes better.
They're out in the generic.
What do you mean it tastes better?
Has a flavor.
It does.
Huh?
Has a flavor coating on it.
Oh, it's got the sweet color.
So out of these, I would say that B would be the correct answer. That the active ingredient has to be exactly the same. But it might have something else different about it. It might be a sugar coating. It might have added to it something else that makes it release into our stomachs slower. So it might be the 12-hour release of Mucinex as opposed to the 2-hour or 6-hour, whatever that is. So you can't say it's Mucinex or whatever that active ingredient is unless it has that active ingredient in it, that exact molecule. But you might have something that acts differently about it because of other things that are in the same combination. the reason I made this question was about 2 years ago. I was hanging out with some of my wife's friends who were like the school idiots at their high schools, and are now pharmaceutical sales reps. They make 5 times my salary, right? They're maybe more than that. And they were trying to tell me that when they go talk to doctors and nurses and people in the field, the medical field, they tell them that, oh no, you don't want to buy the generic of Avastin, or whatever drug they were selling. Sometimes it has like glass in it and stuff, and sometimes it's a different compound.
What? You're literally...
Like, hopefully the doctors will be like, get the hell out of my office.
Yeah, but they're not selling the generic. They're not going to get a commission if they try to,
So, I think it's really important that as people who might be in the medical field, the reason you're in this class, in my mind, is so that when you give someone, a patient, a drug or a mixture of drugs, you have an idea of the things that are in there and how important the number of them are, right, the dose, the differences in the compounds that you end up giving, and potentially the mixtures between those drugs. And the shape and the makeup of those drugs can look really subtle if you read a name and it has a 3 instead of a 2 or an R instead of an S. But that can make all the world of difference with the actual outcome of what the drug is. So today's class, we're going to kind of start thinking about how do we look at bigger molecules? What does it mean to be a bigger molecule? And so we're going to be looking at Avastin as the drug that we're going to be kind of paying some attention to today. And then we're going to be talking about why is it that the different arrangement of atoms ends up imparting them with some different properties. So I want you to be able to, this is some of the stuff we were doing before, right? If you look at a molecule, or an atom in particular in a molecule, I want you to be able to predict steric number, AXE notation. From that, we can determine the electron geometry and molecular shape. And without that, we can't do that next step, and that's polarity. So, well, and along the lines, we also need to be talking about salts, because that relates to polarity. So determining when we have an ionic bond and what the salt is. But so based off of all these factors here, if a bond is polar or not, if it's ionic or covalent, we need to be able to determine that. And then I want us looking at big molecules, because this doesn't make sense if we're just looking at a single bond in something that only has 4 atoms, because you're never going to give that as a drug. So then it's going to be kind of the thing of, is there a net dipole around any molecule in a large molecule? And you can see on the handout today, on the back side of it, of the worksheet, you can see that there is Avastin as a compound, and so I want you to be familiar with what that language means and how to use that. To get us there, let's go ahead and remember where we started or left off last class. So we're on question number 1, I think, on the front side. If we have a molecule and we look at a specific atom, which of these are we going to be able to use to determine the electron geometry? Go ahead and click in your response and then check with your neighbor. Oh, and our learning objectives for today are wrong. Sorry. I didn't copy paste them from the slide. Those are wrong. The ones on your worksheet.
Oh,
If you're using it as a study guide, we're not doing those today. We're doing these ones, which I'll post online after class. All right, coming in strong. Talk to the person beside you. Which one for electron geometry? All right, how do we feel about this? Pretty confident? Like about this confident? Kind of all over the place?
So what's the answer?
So we're basically split. Would it help if we define the electron geometry? Because I think there might be some confusion between that and molecular geometry, molecular shape. So what is the electron geometry? What is it, Lena?
The geometry of the domains, like electron domains around a central atom.
Great. It is the electron domains around an atom that we're looking at. What is molecular shape then? What's the difference with that?
It's the bond.
So if we look at a molecule like Avastin, what is missing in this that we need to think about for electron geometry? Lone pairs. So molecular shape, we're saying where do the atoms end up in space? Electron geometry, we're talking about all domains of electrons, all groups of electrons, okay? So this one I'm saying with all electron domains, which one do we need? So go ahead, talk to your neighbor, try to reassess this question for specific electron geometry. What did you say? From what?
I think A, because the steric numbers.
Why?
Because just from the lab, practicing with the different shapes and stuff, I've noticed that, like, for example, tetrahedral, even though you can have it with all four bonding, or you can have a tetrahedral with one singular lone pair as well. It's like a category of it.
Okay.
And then, like,
Select your answer again. Couple more seconds. All right, I'm going to close that up. Can I get a volunteer that changed their mind and to explain why they changed their mind? We had about 10 or 15 people change their mind. Would anyone be brave enough to share? Kiara?
We changed our mind because we were thinking about, we had to reread the picture, we were thinking about molecular geometry versus electron.
Okay, great. And so now that we're thinking about electron geometry, which answer do you think is the best?
A.
Okay. The majority of the class agrees with you. And you are in the group that switched over. If we know, white ink doesn't help very much. If we know how many domains there are of electrons around the central atom, we can then say where do they end up. How can they repel each other the most to give themselves the most breathing room? So then the next question piggybacks off of that. What about for molecular shape? If we use steric number to figure out the electron geometry, then I want to say, well, where are the atoms in space because of how many are lone pairs and how many are not? Go ahead and click in your response for that.
the number of X and E, does that always do a steric number?
But for oh. There. You have to do extra stuff math. Yeah, you go. Couple more seconds. Closing out. So we have an interesting split between B and D. Would anyone like to argue for one of those over the other? Answer is B over answer D. Donald?
Mine was B, because then you know how many bond pairs there are and how many lone pairs. Because you can't tell, let's say you have a tetrahedral, but you
So water is a great example, right? We have a steric number of 4. You can draw that a whole bunch of different ways, right, for your Lewis structure. But my favorite way to draw it is thinking about molecular shape. If we only knew how many bonding domains there were, we would say, well, 2 bonding domains, so that's linear, right? Is water linear? No, water's not linear. So we can't do that with just the number of bonding domains. We also have to consider, like Donald said, that there's 2 lone pairs. And those 2 lone pairs, the electron pair geometry, or electron geometry, is tetrahedral. But because 2 of those are non-bonding, then that means that we have bent molecular shape. Taylor brought up a very good point, and she says, well, if I want to do an extra step, could I use B to answer electron geometry? And what is that extra step?
It's X plus E.
So if we add up the x's and the e's, we can find the steric number. So yes, if you only had the AXE notation, you could get both from it. But if you had steric number and AXE notation, then it would be quicker to do steric number to find the electron geometry, because you wouldn't have to add anything together. Questions on that? So if you only get to choose one, would you have steric number or AXE notation? You would want to have AXE because you get more information from that. Not only how many domains are there, but how many are bonding and how many are non-bonding, so you can find the total. All right. This is kind of a pattern that I want you thinking about when we're drawing our Lewis structures. If we don't draw the right Lewis structure, then all this is worthless. We can't answer any more questions. On an exam, I'm going to give you a molecule, and you're going to have to go from a formula to a Lewis structure. And then once you have the Lewis structure, you're going to have to answer questions like this. And once you know the shape, the molecular shape, only then can you say whether it's polar or not. So it's a whole process, and if you can't get the beginning, the first step, the Lewis structure, then none of the rest is going to work out. So it's really important to build up all the way. So go ahead and draw the Lewis structure for formaldehyde. And we are going to try to have a pretty quick pace in the first half of class so we can get to spend some time with electronegativity and polarity in class tonight. You get stuck at people around you or right on the thing.
I just happen to have it still right here. Wait, we just did that because I did it right here.
There was one that is a regular. It didn't read the right answer. Because it was, yeah, it's right. They had like
Whatever you had to take, didn't match like what I
Yeah, it was weird. It had like double bonds and I actually saw like 6 against it and I was like, I was looking at it too.
And I tried to like, be more accurate. She said, no, don't do that.
All right. Was that? I saw some people looking back at your lab notes. I didn't realize this is a molecule you had in lab. But even if you have that, I want you thinking through the process. So, what is the process that I want you to go through to start drawing a Lewis structure? So, even before we write the central atom and all this stuff, we're going to do some math. What's the math? So I want us to use S equals N minus H to figure out how many bonds exist in that molecule. This is one of the easiest things you can do to avoid mistakes. And I'll show you a couple examples of kind of where this could lead you to. So if we did N, how many would that be for this molecule? The total number if everything had an octet or duet. 24 sound right? So we have a carbon and oxygen each have 8. That's 16, 17, 18, 19, 20. I get 20.
Yeah, because
Hydrogen only needs 2 each. So, and then we subtract from that how many total valence electrons there are in the molecule. How many does it have? It has 12 electrons. So if we subtract those two, we find that we need to have 8 shared electrons. How many bonds is that? So 8 shared electrons means that we have 4 bonds. And then we go and do a pterosid. We put the least electronegative atom in the middle, carbon, and then we say, okay, well, I know that I have 3 things it's connected to because of the formula. But now I only have 3 bonds. Here's where this will save you. I saw a couple of people go ahead and put a lone pair on carbon to give it its octet. How do we know that that's not going to happen?
because oxygen still needs more. Carbon only has 4 bonds. And it has to have a 4.
So there's a number of reasons why this isn't going to work, but the first and most obvious one is if we knew there were 4 bonds, we would have put the 4th bond to oxygen. So then we deal with the lone pairs later. So we have 4 bonds. They're all drawn out now. We know exactly how many. And then the question is, how many more electrons do we have left? So we've used 8 of the 12 electrons, right? We have 12. We've used up 8 in bonds. So how many do we have left? We have 4 more electrons. Where are we going to put those? 2 lone pairs on oxygen. All right? So one of the things you're going to notice, carbon always has how many bonds? Carbon, every single time you see carbon in this class, or pretty much any class you're ever going to take, 4 bonds. That's not that you can't do a rule like that for a lot of the different atoms, but carbon is 4. We're going to come back to that in a minute. How many bonds does hydrogen have to it? 1. All right, keep those 2 in mind because that's going to dictate what we're going to do next. All right. So I saw some people writing out the molecule like this. What's less than ideal about the way that I drew that molecule at the bottom? So symmetry might be important, but what am I not showing here, Chad?
The molecular shape.
Yeah, I could add some additional knowledge to this by drawing the molecular shape. I know around this carbon, what's my steric number around the carbon? Okay, talk to your, maybe write down on your own or talk to your group. Write down, what are we going to do? Steric number, what else? Steric number, AXE, electron geometry, molecular shape. Okay, write those 4 down. Steric number, AXE, molecular shape, electron geometry.
four,
just around the central atom.
this is three.
Well, wait, would you count that double bond as 1 or 2?
Yeah, I have it because he was
Nope.
like, I'm confused with that.
You want to draw that one? Go through these steps. Steric number. Around the carbon. We can only do this around the carbon, by the way. You can't do this for the other atoms in this molecule.
Number of bonds around a central atom.
And this is questions, well, it leads up to questions 4 and 5. How many bonding lines is All right, so let's go ahead and work through for that central carbon. What is our, can I get 2 volunteers? One to do steric number and AXE, a second volunteer to do electron geometry and molecular shape. So Jocelyn for the one volunteer. Who's the other volunteer? Shelby. Okay. Shelby, you want to go first? Do steric number and AXE. Steric number for the carbon in the middle. How'd you get 4? Not quite sure where you're going. So steric number is the number of domains of electrons around that atom. So if we're looking at the carbon, how many domains of electrons does it have, including lone pairs? Sorry? No, how many bonding domains and how many lone pairs? Total.
4 bonding, 0.
Does everyone agree? Steric number is 4. I see half the people nodding, half the people shaking their head. Why no, Olivia?
I think it's 3 because you count the double bond as 1.
Exactly. How many domains of electrons? This is one domain to the hydrogen, one domain to the oxygen, one domain to the other hydrogen. This domain at the top happens to have 4 electrons in it, but it's still one domain of electrons. So then what is our AXE notation? Shelby, you want to give that one a shot? AX3, E0, but we don't need to write the E0. There's no lone pairs in that oxygen. So going back to what Tay said earlier, we can figure out the steric number because there's only 3 domains and they're all bonded. Okay, and then Jocelyn, what is our electron geometry around that carbon? So there's a triangle, so it's trigonal, and it's all in one plane. Trigonal planar. And then what about the molecular shape? Why? So the questions in this case are identical. Question number 1 for electron geometry. Where are all of these 3 domains? We don't care if they're lone pair or bonding. So 1, 2, 3 domains. They're in a triangle distribution and they're flat. They're all in the same plane. And then it happens that all of them are bonding, so the molecular shape, where are the atoms bonded? They're in a triangle in the same plane. So when do we have these 2 being the same? Does that happen a lot? Sometimes? What do you need to have happen in order for these two to be the same? What was that? I heard someone say it. No lone pairs. If all of your domains are bonding domains, then your electron geometry and molecular shape are the same. Jocelyn? So you can only do all of this for one atom at a time. So we're saying, we're looking at this carbon right here. If I describe this carbon, what's the steric number of that carbon? We're not describing the whole molecule, we're just describing around one atom. So when we say around a central atom, we pick one, and then you can describe all these four things about that one atom in the molecule. Could we describe hydrogen with all these as well?
Yes.
No.
What?
We can't, because it doesn't have a molecular shape. It doesn't have an electron geometry, because there's only one thing coming off of it, so you can't describe it.
But if there was another thing coming off of it, you could describe it.
Let's look at the oxygen. Can we describe oxygen with all four of these?
Yes.
No.
We can describe steric number. It has 1, 2 lone pairs and a bonding domain, so that's steric number of 3. AXE we can do, right? 1 bonding, 2 non-bonding, AXE2. We can do electron geometry, trigonal planar. But can we do molecular shape? No. This doesn't work because we need to have more than one bond. Otherwise, there's no shape. It's away from me. Like, that's not a shape.
So the E on that AXE is only around the central atom?
So anytime we ask for these four things, we have to say around this one atom, what is there? And I could say this one. I could go in a molecule and I could ask you for steric number, AXE, and electron geometry around that oxygen. I just can't ask for molecular shape because it doesn't have one. So we'll get to a bigger molecule in a second. You'll see how that works.
Would you ask, like, in H2CO, would you do, like, what is the AXE and
I couldn't say, here's the molecule, what's the AXE? It doesn't work like that. You have to specify the atom in a Lewis structure. So I could either ask you to draw a Lewis structure, or I could give you a Lewis structure and say around the oxygen, what's the AXE notation? Josh?
Why wouldn't, if you're just looking at the oxygen, why wouldn't the oxygen part, why wouldn't it be linear for the molecular shape?
Because linear means that it's in between two other things. And so because it's only by itself, and there's only, so there has to be something here as well to be a straight line. That's a good question. All right. And I think we've already answered these. All right. Let's talk about bond angle. If we look at the HCH bond space, you know what I'm talking about in this molecule? Between the H, the C, and the H, there's an angle here. What is the ideal bond angle? Do we know what we're comparing that to? So there's ideal and there's actual. The ideal is just based off of the steric number. And then the actual is some domains of electrons have more repulsion than others. So what is the ideal? Go ahead and click your ideal, the ideal bond angle for that HCH. 5 or 10 more seconds. All right, closing up. A vast majority of students in this one said if you divide a circle in 3 parts, you have 120 degrees. So this angle right here is a third of an entire circle. It's 120 degrees. So I concur with the majority of the class. So next the question then becomes, is it exactly 120? So the first one was theoretical, which is not considering what these are. And now I want to say, what is the actual bond angle? Do you think it's going to be a little bit higher than 120? Is it going to be a little bit lower, or is it going to be exactly 120? Go ahead and talk to your neighbor and then click in your answer. have shape.
What are you looking at from the ages of the O's or from the ages, or from ages to the ages?
Couple more seconds. We have an almost 50-50 split. Actually, it's probably 40-40-20 split. So the question, are we comfortable with these symbols? No, I say that, but I'm not trying to make fun of it. I have had students come up to me in exams and been like, I've never seen that symbol, or I don't remember what that symbol means. So what does this top symbol mean? Greater than. So the number is greater than 120. It's on the bigger side of the wedge. This number is less than. So the number we're talking about would be less than 120 degrees. All right? So we have a split between these answers. What gives? Can I have someone who's confident in their answer, or their group's answer, maybe share their discussion? Savasia, go ahead.
I say less than 120, just because the oxygen has that double bond. I feel like it's pulling the carbon, so even though the hydrogen don't want to be close to each other, but they have no choice, because the carbon is pulling that way.
So you're combining a couple of different concepts, and so let's separate those out. So what is the reason why these spread out as far as they can away from each other? So electrons are negatively charged, and we have electrons in this bond, and in this bond. Okay? So the electrons are repelling each other, and it's not about an attraction, it's about a repulsion. Vesper, that R is for repulsion, right? So then the question is, how do the double bond, how does that bond interact with the single bonds, and how do single bonds interact with each other? They're all repelling each other. That's why they're overall about like that. But does any one group repel the others more? I hear some yeses, I hear some nos. Who wants to volunteer to raise their hand to explain why you think it might be a yes or a no? New voices? Dylan?
The double bond of oxygen to the carbon would be stronger than the individual bonds that the hydrogen makes for the carbon, and the hydrogen has lower electronegativity.
So we're getting into electronegativity, which is a topic we're not even talking about yet. So we're specifically thinking about which bonds repel each other more. And that's, I think, where Savasia is going to, but I don't want to do that. We're going to separate it out completely. Which of those sets of bonds might repel more than others? Or are they all equal? Bradley?
So in a double bond, you got 4 electrons, and in single bonds, you got 2, so therefore you have more electrons to repel against the lesser amount.
What do you think about that?
Sounds good.
Sounds pretty good to me, too. So you have twice the number of electrons between these two atoms as you do between these. So this is going to be a higher density of electrons, which is going to push both of these in a little bit. So that means that bond angle is going to end up being less than 120.
I put the wrong
Okay? So what groups have more repulsion? Is a lone pair more repulsive than a single bond? A lone pair is actually more repulsive than any number of bonds. So if we had, I'm just going to draw some makeshift molecule here. I'm going to put A in the middle, and I'm going to do a lone pair. What's the steric number around A? B3, 1 lone and 2 bonding. What is this theoretical bond angle? It's 120 because we have 3 different domains. This is about 120. But is this bond angle right here going to be the same as this bond angle or less? Is this going to be less or is this going to be less?
They're both less, aren't they?
They're both less than 120. Which one is smaller of the two that are less than 120?
Yeah, bottom was the bottom.
The lone pair has more electron density than the double bond. And it's because this isn't stretched between two atoms, it's just sitting right on top of that atom. And so that negative charge density actually repels these to a greater extent than even 4 bonds, or even a triple bond if you had 6 electrons in there. All right? So what do I need from you guys? On an exam, I need you to tell me what the ideal bond angle is. So it would be 120 for this particular, because we have steric number 3. And then to say, based off of a double bond or a lone pair, is the actual bond angle going to be slightly higher or less? That's where it ends. I'm not going to necessarily give you these two and say which one is a little bit more than the other. I just want you thinking about that. All right, go ahead and draw the Lewis dot structure for propane. And we're going to probably need to start picking up pace, so I'm going to give you about 2 minutes for this. You can tell some by how the formula is written out. So go ahead and take 2 minutes to draw this. Does it have the right number of electrons? Are there any double bonds? Do you know how many bonds it should have?
God bless you. I felt so proud sticking, like putting them together.
Sometimes that'll work. Sometimes it won't.
How'd you do it? I felt
Then you're doing S equals N minus H.
my
How many bonds should you have? You don't have
Ow.
to do it.
I felt like my super fancy when I did it. Is that not it?
All right, we're right at about 2 minutes. How many bonds should we have? Did anyone do S equals N minus H?
That's the part that confuses me. That
S equals N minus H. What is our N in this case? We have 3 carbons. How many electrons should carbon have if it's an N? Should have 8 each. So that's 24 plus how many hydrogens do we have?
we have 3, so that would be.
We have 8 hydrogens.
Oh yeah.
Oh, we're doing the full one, aren't we?
8.
Yeah, there we go.
And then we have 12 plus 8 electrons as our valence. So that's, what, 40 minus 20?
Wait, how'd you get on? Oh, that's the thing. I see.
Am I on? Carbon should have 8 electrons each. There's 3 of them.
Well, what's that other?
Hydrogen should have 2 electrons each. There's 8 of them. Carbon does have 4. There's 3 of them. Hydrogen does have 1. There's 8 of them. So that's 20 minus 40, or 40 minus 20. So that means that we have 20 shared electrons. So how many bonds is that? So if we just go ahead and try, which I saw a lot of people do, which I don't mind as a first step, just like, let's just draw everything connected out. How many bonds is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done.
Bam.
No lone pairs. Don't need to think about anything else.
Oh.
Because we counted all 20 as shared. We only had 20. So we're done. Okay? If we had come out and said, oh, we actually need 11 bonds, we would have to figure out where to put an extra bond in there. What's one way we might have been able to be comfortable not doing the S equals N minus H for this one?
Because, you know, H's only have one bond.
H's only have 1 bond, and how many bonds does carbon have?
4.
4. So if you had just gone ahead and drawn this and been like, well, carbon has 4 bonds everywhere, then I know I don't need a double bond because we couldn't add any more bonds. So, here is our Lewis dot structure. Go ahead and draw the line structure for propane. Not the Lewis structure. I just drew the Lewis structure, right? What's the line structure? Skeletal structure, you could call it. 30 seconds.
Same structure. That's what we just did. Quick consult Google.
All right. Looks like everyone's got it. We don't need to worry about it.
What? What? Oh, what?
This is propane. This is the molecule we just drew. Remember earlier, like last week, you guys laughed at me when I said the chemists like to do things as simple as possible? We don't like to put in a lot of extra effort. What are the most two common elements that you'll see in any chemical structure? Carbon and hydrogen. So we came up with a system. Like, okay, if there's a carbon, we're just not going to draw it. If there's a hydrogen, we're not even going to show it. How does that sound? So, what is at the end of each one of these lines? A carbon. Let's just start there. What's at a point where the line changes directions? In the middle of the molecule, carbon. And on the far end, carbon. 1, 2, 3 carbons, right? 1, 2, 3 carbons.
Wait a minute.
And then we say, so basically we're doing this. Carbon, carbon, carbon. Okay? Wherever a line starts, changes directions, or stops, is a carbon. But then, what was that rule we just talked about with carbon?
It has to have four.
Always has to have 4 bonds. So if we don't show 4 bonds, then we know that's how many missing hydrogens there are to get to 4. How many bonds does this carbon have drawn to it? It only has 1 bond, so how many hydrogens are on that carbon? 3. So this one has 3 hydrogens. What about the one in the middle? How many bonds does that have drawn to it? 2. So how many hydrogens are missing? 2. The one on the far right has how many bonds? There's only 1 bond shown. We have to get up to 4. So this is another language.
I mean,
Sebastian?
is it that going to be a test?
But there wouldn't have those
Yes.
things on there.
So I don't know if you've noticed my class time. I don't use for anything that you don't need to know. I don't just like pontificate. Maybe the first question of today, but I'd argue that that's setting the stage for
This
today.
would be on our test.
That was the question, is yes. I will examine you on this because I think it's really valuable.
Exactly.
We're going to practice, okay? This is the first step. So, let's practice. Let's skip that. So flip over to the back page. We're going to look at this molecule Abilify. And we're going to combine a few things. Remember, that line structure that we just used is the basis for this. So what's right here where my finger is?
Carbon.
What's right there?
Carbon.
Anything but carbon will show
I'm
you.
at the point.
We're at the intersection between these 3. What about right here?
Carbon.
Here.
Oxygen.
Okay. You get the drift. So where I'm pointing at, that's a carbon. I want you to tell me what is the molecular shape around that carbon. Go ahead and talk to your neighbor. Try to figure it out. And then go ahead and click in your answer.
It has to have 2 what out there? 2 syllables. It has 2 bonds. It needs 2 more.
I always thought they drew this to look like
Okay.
compounds.
So if
So
I
I
was
saw this
right
on
here.
Wikipedia was looking at the
Why
drawing.
does it need 2 more? It needs 2 more. Like what he did on that. Yeah, like the thing, but then it had like out here. So it's got 2.
All right, a couple more seconds.
That would mean it's a carbon with, I don't understand. Oh, it's got two hydrogens on independently.
Yeah, that's what I was like
So
showing.
that's linear, right?
Yeah, like you have your, like you're pointing to this, and you have a bond here. And you have to
I mean, carbon follows the rule no matter what.
Oh
So,
crap, my thing is off, don't turn it off.
all right. Submit an answer. Answer needs to be submitted.
The line inside still,
that I don't know. That's probably gonna.
And I'm closing out. All right, we are all over the place. So let's start out here. Is there anything that isn't drawn that might be really useful to answer this question?
The what?
So we might need those at some point, Carmen, but maybe not to answer this question. Donald, what are you thinking? Do we have a lone pair in that carbon? No.
I'm gonna say the hydrogens are not.
I'm only seeing.
So we don't show lone pairs in skeletal form, which this is. That's true. Have you ever seen a carbon with a lone pair on it? What's the rule? Carbon has 4 bonds. I didn't say 4 domains. I said carbon has 4 bonds. If you ever end up taking organic chemistry, you will find that there are rare exceptions where you actually have a lone pair. But outside, in this class, you will never see that. Carbon has 4 bonds, so what's missing? 1 or 2 bonds? How many bonds are shown to that carbon? 1 down and 2 up to the left. So that carbon has a hydrogen that's not shown. Okay, so then let's go through the steps. Steric number is 3. 2 single bonds, 1 double bond. AXE. AX3. All of the 3 domains are bonding, right? Hydrogen, carbon, carbon. What's the electron geometry? So we said steric number equals 3. It's AX3. None of them, we don't have any lone pairs, so that means what? If there's no lone pairs, molecular shape and electron geometry are the same. And with a steric number of 3, we know that that's trigonal planar. This is what you're going to be able to do on the exam. You're going to have to do in the exam to answer Sebastia's question. You want to do another one?
Yes, please.
All right.
I didn't have time to read it.
Okay. Now I'm pointing at the oxygen at the bottom, and I want to know what is the electron geometry around that oxygen.
Are you supposed to be looking at the lines that are touching it? Like, what are you looking at?
So the lines touching it are how many carbons?
Would each line represent 1 carbon? Is that like?
There's a carbon at that intersection. There's a carbon.
So you're looking at this, the crease, not the line itself. So this here would be there's 3 carbons.
This is 1 carbon. This is 1 carbon. That's 1 carbon.
So it's surrounded by 2.
All right, 10 more seconds. Closing out. Make a decision. Closed. Our answers are all over the place. Let's go back to that first question I asked for that carbon. Is anything missing for that oxygen? What? How many lone pairs? How do we know that it should have 2 lone pairs? So I heard a term that I love, the octet rule. Someone already drew this Lewis structure, and it obeys all the right rules. So we just have to say, what's not being shown? What's not being shown is the carbons, because that's where the line changes directions. We're not seeing the hydrogens, and we're not seeing the lone pairs. So whenever we see oxygen, we almost always see 2 bonds and 2 lone pairs. Whenever we see nitrogen, how many lone pairs does that almost always have? Nitrogen almost always has 3 bonds and 1 lone pair. It has to get to that octet, and nitrogen almost always has 3 atoms bonded to it. Okay, so now we have 2 lone pairs and 2 bonding domains, 2 carbons it's attached to. So I'll just write in the C's here to make sure we know this attached to those. So can I have someone tell me what the steric number of that oxygen is?
3?
I hear 1, 2, 3, and 4.
It says 4.
It has 4 domains, 2 bonds, 2 lone pairs. What's the AXE, Cassandra?
It would be AS2E3.
Because 2 of the 4 steric number are bonding, 2 of them are lone pairs. And then if we go to the next step, what's the electron geometry? Is that based off of the steric number, or do we need to know how many are bonding and non-bonding?
Be bent.
Steric number is enough. So what is that? We could do molecular shape too. I didn't ask for that in this particular question. Is that what's asked next? Let's see if that's the next question. Yes. So now, I want you to decide, we know the electron geometry around that oxygen. I want you to tell me what is the molecular shape around that. Let's do 10 more seconds. All right, everyone's in. Can I have a volunteer? New volunteer who hasn't spoken yet? What did you answer and why? Jay.
Okay, I'm sure that's it. So, the bed, it looks like 2 bonds and this one does too, like the line, and then it has 2 long pairs, so it gotta be bent.
It's got to be bent because if we go back in and add those lone pairs, however you twist it, we're saying where do the atoms end up in space? They have a bent shape. Great. I agree. You getting the hang of this? So what I want you to be able to do is I want you to look at a script and Google the structure of a molecule that you're going to give to a patient, a drug. See a structure like this and be like, oh, okay, I know how many carbons there are, how many nitrogens, how many hydrogens, how many oxygens. And to be able to count those, to be able to understand what it means with how they're connected. And so we're going to spend a bit of time, we're going to do one more thing, and then we're going to talk about polarity. Polarity is really where it becomes important. Could you do this with any molecule I give you?
No.
You want to do one more really quick?
Yes.
All right, we're going to do this with speed round, okay?
Oh, no.
Nope, that was not. That nitrogen at the bottom, what's the electron geometry around that nitrogen? What's the first question you ask yourself? Is anything missing? Right? You have to fill that in first if anything's missing. Ten more seconds. And coming across the finish line.
Wait. I got it.
These questions, are they like on the blackboard? The clicker questions?
I will post these slides after class like I do every class, and it's on the recording as well. Okay. There was a point in time at which we were a 50-50 mixture. One of the answers did win out. what might be a reason why we would answer this question as trigonal planar, and why might we answer tetrahedral? Those are the two main answers. If we counted the lone pair or not. How many bonds and how many lone pairs does nitrogen almost always have? Nitrogen almost always has 3 bonds and 1 lone pair. So if you see nitrogen here, it's bonded to a carbon, and a hydrogen. What's a little bit weird about this one, I will give it to you, is it doesn't look like it's bonded to this hydrogen. Sometimes we get lazy with nitrogen, and so whenever we see NH, that means N bonded to H. Okay, so that might help clarify things. So it's missing the lone pair. What's the steric number? 4. Which means, just from that alone, we have tetrahedral electron geometry. If you didn't know that it had a lone pair, steric number is 3. And then you would have said trigonal planar, which was not correct because you didn't include that lone pair. Dustin?
Why is that hydrogen shown?
Because if nitrogen can have more than, it can have 3 or 4 bonds. You'll see it in a minute. And so if we have a hydrogen attached to anything besides carbon, we show it. Hydrogens are only implied attached to carbons. Good question. So if this oxygen was attached to a hydrogen as well, we'd have to show it. If this nitrogen was attached to a hydrogen, we'd have to show it. All right, and last one, molecular shape. Go ahead and select your answer of that nitrogen. Looks like we're almost there. And we're closing out. All right. We had a vast majority answer one of these answers. Would anyone like, who's somewhat confident, to share their answer? Carmen?
Okay. I put the trigonal planar because it has 3 bonding and 1 lone pair.
Okay, so you said it was trigonal planar. Does everyone agree with that?
No.
Did you say pyramidal?
What did you say? I meant to say
Okay, maybe I misheard you. Sorry. So if it has no lone pair, it's AX3. We're here, but it's AX3E. So it's a pyramid-shaped triangle. I agree. And that was the majority answer. Okay? You're doing great. And so, how would you practice this on your own? I mean, I guess you could. Go into your medicine cabinet, or with things that you're doing for your nursing classes. Don't take them. Google the structure. Google the structure of ibuprofen, of acetaminophen, of Aleve, of hydrocodone, whatever different compounds you want to look at. Pull up their structures and go around. In Wikipedia, you'll find the structure, and then try to name electron geometry and molecular shape, steric number AXE, for every single atom in a molecule. Where are the lone pairs not shown? Where are the hydrogens not shown? And that'll be perfect practice for the exam, which is in 2 weeks.
Is this going to be, will there be like practice doing this with the dynamic stuff?
No, there will not be. So this is a part of the class that I think is vital. If you leave this class and you cannot look at a structure and been like, oh, I know something about it, then in my mind, you should have, like, I can't justify you ever took a chemistry class. To me, this is chemistry, is like looking at a molecule and knowing what that means something, and it's a language, and you can explain what that means, and then you can look at 2 different molecules and know something different about the 2 of them.
By looking at them.
By looking at the structure, not by taking them. Okay, question. We didn't go as lightning as I wanted, so we have 11 minutes left of class. Do we want to, A, work on naming of ionic compounds in a little bit more Lewis structure? Or B, do we want to talk about polarity?
Polarity.
Okay. You guys want a chemistry jug first?
Yeah. They mentioned a freeze walk to the bar.
Okay. It was a sad lone pair. So here is Taxol. Have you heard of Taxol? Chemotherapeutic, actually very complicated drug, complicated molecule. This molecule, because of how it's arranged in 3 dimensions, and by the way, these dashes, have you seen these yet?
No.
These dashes and these wedges are trying to show 3 dimensions. So the dash means that this bond is actually sticking back away from us. The wedge means that it's sticking up towards us. Okay, I'm not going to necessarily give you questions with that on the exam, but I want you to know that that's a little added layer of texture in the molecule.
What are the lines inside of the little, what are those called, pentabonds? What are they, what are those little lines inside they're called?
These? They're just bonds.
No, not those inside of it, like there's 3 lines inside of it by themselves, you see them? They're like,
Oh, there's a carbon here, CH3, and there's a CH3.
oh, not that, no.
Okay.
Like
I
the
don't know.
bottom.
The
Like
bottom?
one.
These are double bonds, single bonds, double,
Oh,
single, double,
bonds.
single.
Okay, here.
Okay, so why does Taxol do what it does? It's a microtubulin stabilizing agent. It keeps our cells from being able to reproduce. And the reason is because that molecule, it doesn't exist, it's flat on a piece of paper. It turns, and then certain parts of it are more attracted to parts of tubulin. And so you can see some of these rings. That ring is, I think, this ring here. And so that ring, as it sits in space, is attracted to this part of a protein. And that's because of polarity, or a lack of polarity, actually, in that case. Or there's polarity here, where there's an oxygen. So that oxygen is this oxygen here. And so that oxygen has a polar bond attached to it, and so that's attracted to part of the protein over here. So all of the interactions that we have in chemistry and in biology are because one molecule is polar or charged, and another molecule is polar and charged, and then those then attract each other. Pluses attract minuses, neutral attracts neutral. So what I want us to start thinking about is, where does that come from? Where does that originate from? And it's this idea of electronegativity. So on one of your sheets, the back side of one sheet, you have this. It's called Pauling's scale of electronegativity. What is electronegativity? I'll give you my definition, then we're going to have to work with it, all right? Electronegativity is if we have 2 atoms that interact with each other. How strongly is each of those atoms going to try to pull any shared electrons towards itself? The bigger that number is, the stronger the pull is. So if you have 2 things that have the same pull on electrons, which one of them is going to win that battle of tug of war?
If they're the same?
They're the same.
Wouldn't it be non-polar? If they're the same?
Neither one's going to win the battle. It's going to be non-polar. Polarity comes in when you have one that has a much stronger pull than the other. And if we get to an extreme where that pull is insanely different, if we get something that's from here and from here, we put those 2 together, that's going to be such a strong pull that we say the more electronegative one, the one with the bigger pulling power, actually steals that electron, and it's not even sharing anymore at all. It's ionic. So let's look at a definition of what is polar and what is not. And I had a pen. And I want you to do this as a clicker question. I want you to look at all of these 7 bonds, and based off of the difference in electronegativity, so we look at carbon, 2.5, hydrogen, 2.1, I want you to say, are these going to be polar, yes or no? If they are, what's that? If it's going to be polar, I want you to put in 1. If you think all 7 are going to be polar, put in 1, 2, 3, 4, 5, 6, 7, enter. If you think it's only 1 and 3, hit 1, 3, enter.
Oh, okay.
Okay, so there's a lot of numbers, so it's not multiple choice. It's multiple select. Which ones are going to be considered polar? What are we using as our guide to determine polar?
Well, you said one if it's not polar and two if it's polar, or you just.
No, you're just saying if you think 4 is polar, then you enter 4 and hit send. That's all.
Oh, right.
But what difference in electronegativity makes it polar?
It has 3, 4, 5, there it is.
You see our scale up here? Everyone catch that? And after you hit send, check with your neighbor too. See if you have any discrepancies. Enter the numbers that are polar. Did you notice there's a number line right below it? One thing that might help is you could put each of the bonds on the number line between 0 and 4. See that number line there? What is the difference between the two electronegativity values of those compounds, or those elements? Oh!
I still don't see a number line. What was that number line?
On the bottom of our worksheet.
All right, we're running low on time, so let's talk through this. How did we figure out which ones are polar and which ones aren't? We find the difference through subtraction of the electronegativity values. So, are there any we can cross off without even doing any calculations? Anything and itself. Those are not going to be polar. So, if I have my number line, which I'll show on the next page, then we put those at the far left. The difference, right? Delta means difference. Delta is difference. That's a weird dog's name. So, how big is the difference in electronegativity between the two? What about C and H? Is that polar? Difference is only 0.4. We're going to say that that is nonpolar. And then the rest of them, we find a difference between nitrogen and hydrogen, oxygen and hydrogen, that's 0.9, 1.4, C and O is 1.0, C and N is 0.5. So all of those are considered polar. What you're going to find with organic chemistry, if we go back to that molecule we were looking at a second ago, really what it comes down to is anytime we see an oxygen or nitrogen, unless they're attached to themselves, that is going to be a site of polarity. It's a really easy way to kind of narrow it down. So the last thing I want to do here is up to 0.4 on the number line. We call that nonpolar, right? Up to 1.9, we call this range in here polar. Both of those mean that they're sharing electrons. The question is, are they pulled more to one side, being polar, or are they very close to equally shared, being nonpolar? And all of those types of bonds have one specific name. What do we call those types of bonds? That is covalent. That means that they share electrons. then anything that has electronegativity difference of greater than 1.9, and these are rough numbers, there's exceptions to these always. What's everything called over here on this side? Okay. Those are kind of the three words we use to categorize. Ionic, which is everything over here, and then covalent has two categories. We don't have enough time today to get into the three-dimensional, what this means, but what I want to do in class next time is to look at molecules and say why are some polar molecules and why are some not. I think I'll look at the homework. If there's questions on this in the homework, I might have it due Monday night. So you can try them, but you don't have to do them until we're in class, and they should be relatively easy. Maybe Tuesday. All right. Have a good night.